Tuning in, this is chapter 2, problem 65. Okay. So this whole contraption right here, I drew it as one piece, and so I would treat this whole thing as one object, so weight of ceiling, pulley, whatever symbol you want to use for it. And then up here. And technically there's something holding the ceiling up, but you know, you got to stop somewhere. All right, so let's concentrate on the parts that actually matter for this problem. These two things right here. So, if he is in equilibrium, what do I know about these three forces? I've heard bits of words.
The net is 0.
Okay, so in terms of how does that play out then? What does that mean in terms of, I got three forces here. If I gave you two of the numbers, could you find the third one? How?
You would set all 3 equal to 0 and then solve for.
When you say set all three equal to 0, what do you mean?
Like the adding them all up. The sum of all the forces.
So Ft plus Yp plus Wp equals 0?
Minus W.
Okay, so the forces, so that, or the force, the total force up equals the total force down. Now, as he pulls harder on the rope, this increases. His weight is not changing. So as he pulls harder on the rope, what has to change? What's it going to do?
Decrease?
Yes. And if you've ever pulled on a rope that's hanging from a ceiling, I'm thinking gym class or something like that, you pull on it, you feel a little bit lighter on your, you feel lighter, your apparent weight would drop, not your actual weight. So over here, if this weight is in equilibrium, what do we know about this?
Would have to equal the person. Wouldn't the weight of the weight have to equal the person?
We're getting there, looking for justification for that. Not connecting it quite yet. So, tell me about these three forces. What equation would I write with these three forces?
Same one.
Different subscripts. So Ft plus Y1 is equal to W1. Total force is up, equal to total force is down. So as tension increases, his normal force will drop because his weight stays the same. Over here, if he increases the tension on his side, that means this tension goes up. That weight is not changing. And so what's happening to the normal force between the weight and the ground? At what point, if this over here is decreasing, at what point does it disappear?
When the tension equals weight,
Of,
the mass of the, yeah, that.
okay. So if this is 0, then the tension equals the weight of that. Now back over here, if the tension equals, so if the tension is equal to the weight of what we're hanging out over there, what is the maximum value that this can be? So he's pulling harder on the rope, he's increasing the tension in the rope. He eventually gets to the point where, oh, sorry, read the wording of the question again. Upper limit of the weight the strong man can lift. I think I actually approached it from the wrong point of view. I should start over here. So, over here. So as he pulls on the rope, if he pulls hard enough, what is going to happen to him? if you've ever tried to climb a rope, if you pull hard enough, what's gonna happen?
Gonna fall. He's gonna fall.
Sorry,
He's gonna fall.
Let's start with
I was thinking of going up instead of falling. That falling comes next after going up. So if, as soon as he comes off the ground, what must be true?
He's reached the max weight he can pull.
Okay, I was thinking over here,
Max tension.
okay. You're dancing around it, your mind reading skills are off today. The normal force is 0. As soon as he comes off the ground, his normal force is 0. So his weight here is equal to the tension. So this is the weight of the person, plus Y1 is equal to W1. So the biggest that weight 1 can be is when the normal force drops off to 0. In other words, the biggest weight he can lift is his own weight. That's my justification. It's apparently much longer than I originally intended. Roundabout way of getting to your answer. All right, you want to ask your question again, or are you good to go?
So it's just that because the normal force is 0, then the tension would then equal the weight.
Yes.
Okay, and then that means that he could only lift as much as he weighs.
Right. If he were lifting more, let's say he weighs 100 pounds and the weight is 200 pounds. If that thing is off the ground, if that 200-pound thing is off the ground, then that's going to pull him up. All right, this being said, now let me contradict it. That's the intention of the problem, is that's in equilibrium. He pulls it up and he maintains it. However, if I've got a mass there, if I give a really hard pull to the rope, I can get it off the ground temporarily. I can exceed that. So my tension can exceed my weight. I'm going to accelerate upwards. If I pull hard enough, if I pull more than 216 pounds up, I'm going to come off the ground. But I can exert a tension greater than my weight. I can't maintain it because once I'm off the ground, that tension is basically, I guess I could keep climbing the rope. But it is possible to exceed your own personal weight for a temporary bit of time. But the intent is maximum is his weight. Any other questions on this one? Other questions from chapter 2?
For 27, so would we do like force to the right? Will we do force to the right equals 350 newtons I hat, or would we just add it up in an equation and solve it?
For, you said 27, Lucy Lightfoot on the scales?
Yes.
You
Or would you just come up with it by just looking at it?
just add it up. Although technically weight is a force and therefore should have direction, Hewitt's intent there is magnitude of weight.
Okay.
If you throw a direction into it, it's not inherently wrong. I'd probably go, oh, that person recognized it was a force, kudos. Other questions from chapter 2? All right, let's get this done. When you're done, just bring it up. If in doubt, show your work, please. You're welcome. There's the power. Reminder, no classes on Monday or Tuesday of next week, Labor Day. So Monday, we did a bunch of conceptual stuff with describing motion, but I could just feel that all of you are hankering for some more math, something where you might need to use a calculator, so let's do some of that stuff. A car travels along a straight line with an initial velocity of positive 20 meters per second. It accelerates uniformly at negative 5 meters per second squared for 7 seconds. I did put A with a vector symbol over it here, but I shouldn't have to because I said the acceleration was negative. And if it's a scalar acceleration, it won't be negative. Actually, I'm going to amend that. It actually could be. Acceleration. Scalar acceleration could be negative. All right, so it's the vector acceleration, negative 5 meters per second squared. And the problem takes 7 seconds. And then we have a series of questions. And again, in case my handwriting is not completely legible, what is the car's final velocity? What is the car's average velocity? What is the car's displacement? At what time does the car stop? What is the distance the car travels? And what is the car's average speed? All right. And you can be sure that on the first test, there will be something similar to this. If you look at the old test, you'll notice a pattern of, hey, he keeps kind of asking these kind of questions every year. So at this point, there's, at least 3 of the types of questions that will be on the test. There's going to be something like this. There's going to be a complex force diagram, and there's going to be one of those motion positive, negative, 0 for the 4 basic functions question. All right, so let's start out with initial velocity of positive 20 meters per second. What does that mean?
For every second it's traveling 20 meters.
If he did not change his velocity, okay. One more piece of information is given there.
It's in a straight line, one direction.
More specifically, we're almost there.
It's not changing
No, it is going to change, but
the direction.
what direction is he moving in?
Positive.
Yes. So if the acceleration were 0, then he would be traveling 20 meters every second in the positive direction. The key thing there is in the positive direction. So I'm just going to do a small little diagram here and then say that to the right is positive, and so the car is initially traveling that way at 20 meters per second. Now acceleration is the change in velocity over the change in time? Or if you've had calculus, dv/dt. Just a side note. Which means that if my acceleration is -5 meters per second squared, that is the equivalent of my velocity changing -5 meters per second every second. So if I set up a little chart here, I have time in seconds and I have velocity in meters per second. The problem lasts for 7 seconds, so 1, 2, 3, 4, 5, 6, 7. Initial velocity is 20 meters per second. How fast is the car going after 1 second? Let me reword that. How much will the velocity change each second?
By -5.
So therefore, after 1 second, how fast is the car going?
15.
After 2 seconds, how fast is the car going?
10.
After 3 seconds? -5. So acceleration is telling us the rate at which the velocity changes. So the car's final velocity, well, we just got that, -15 meters per second. Questions about the -15?
Does that just mean it's going in the opposite direction because it's negative?
Yes, it does. Matter of fact, this car is going to reach some point, stop, and then start cutting back, and end up still on the positive side, I believe. But we'll get there. I could have also done this for those more algebraically inclined. Looking at this, I know that acceleration is final velocity minus initial velocity divided by time. So I could have just gone for the straight algebra approach. And so I have -5 is equal to v final minus 20 divided by 7. Multiply both sides by 7. I get -35 is equal to v final minus 20. Add 20 to both sides. And v final is equal to -15. The math background for this group is a little bit higher than average from previous 110 groups, so this might be more comfortable for some of you than this. All right, average velocity. What is the average velocity? Or how would you find average velocity? How do you average numbers? Well, I got a bunch of numbers right here. What's the average of them?
Add them all up and divide them all. 7, 8, yeah.
Yes. The most common mistake for people who do it this technique, where you add them all up, is they divide by the number of seconds, not by the number of numbers. So if you add them all up and divide by 8, what do you get? Do the full thing. 2.5 what?
Meters per second.
So why'd you add up all 8 numbers? I assume that you added up all 8 numbers. Or, Jay, did you do something else?
No, I don't.
Why all 8?
Because they're all the points of time that you need to know.
Suppose instead of listing them like that, ooh, I should have picked an even number. Yeah, I was, usually do something else, but I usually pick an even number for the time. I want to keep it at 7 seconds. Let's just do a sidebar then. So let's say I have time 0, 1, 2, 3, we'll just go 4 seconds. A velocity in meters per second, time is in seconds. And we'll start this out at 50, and acceleration is -10 meters per second squared. So if my initially is 50 meters per second and my acceleration is -10 meters per second squared, what's my velocity after 1 second?
40.
All right. So my average velocity is Did you get 30 meters per second? All right. Because you got 5 numbers there, it seems natural you would add all 5 up, and that's perfectly fine. But is there anything special about every second? Suppose instead of listing every second, I listed every 2 seconds. What's the average now? Yep, still the same. Matter of fact, what's so special about 2 seconds? Why not every 4 seconds? What's my average now? So if acceleration is constant, then you actually can find the average just by averaging the first and last one. 20 plus -15 over 2, which is 5 over 2, which is 2.5. Now the first technique where you added them all up, where you added up all 8 numbers and divided by 8, something like that works as long as you're going by by some regular interval of time. So we went by seconds here, 1 second. But if I had done 0 seconds, 0.5 seconds, 2 seconds, at that point that technique does not work. So you have to go by, the difference in time has to be the same all the way down. Or just shortcut it and take the first and the last one, which works regardless of the rest of it, if acceleration is constant, which it is. All right, so average velocity, positive 2.5 meters per second. All right, car's displacement. In other words, where does this car end up relative to its starting point? Well, if you travel 50 miles per hour for 3 hours, how far do you go? 50 miles per hour for 3 hours. How'd you get that?
50, 50 plus 50 plus 50.
Oh, you added it up?
Yeah.
Suppose you went 50 miles per hour for 1,230 hours. You can add them all up?
What's that have to do that?
I'm not doubting you can do it, but is there a shorter way of doing it? Yeah, multiply. All right, so if you know what the average is and how long it takes, then you can just multiply them, which is what I was figuring you were going for. So the car's displacement, well, I'm going on average 2.5 meters per second for 7 seconds. What's my displacement?
Seventeen point five.
So my displacement, or x, or whatever letter you happen to be using, is just my average velocity times time. Which also stems from velocity, is the displacement divided by time. So basically the same formula here. So this is 2.5 meters per second times 7 seconds, and you get 17.5 meters. Positive 17.5 meters. Which means that in my drawing right here, if that's my starting point, my final end point, that's 17.5 meters. He's still on the plus side of it, he's just, it so happens he happens to be heading towards the starting point. All right, at what time does the car stop?
4 seconds.
Yes, how do you know that?
It's that velocity at 0.
Yep. Now you do have a chart right here where you happen to hit 0. It doesn't always work out that way. We could have done it differently. Looking at this equation right here, I want to know what time it stops. So in other words, I'm trying to solve for time. So a more algebraic way is my acceleration is -5, my final velocity is 0, minus 20, which is my initial, divided by time. And so we're solving, so we have -5 equals -20 divided by time. Cross multiply, and you get 4 seconds that way. Again, for those who are more algebraically inclined. So, redrawing my absolutely incredible, spectacular diagram right there, just to give myself some more room. So it goes out here, so this is time is 0 seconds, and then at 4 seconds it stops and starts coming back, and the problem ends at 7 seconds. My velocity starts out at positive 20 meters per second. It's 0 meters per second here, and at 7 seconds, it is negative 15 meters per second. And then in terms of displacement, well, that's 0 meters for displacement, and this point right here would be 17.5 meters, positive 17.5 meters. And to the right is positive. Questions to hear before we talk about distance? All right, so the distance that he traveled. Well, he shoots past the final position, and then comes back. So I need to figure out, well, how far does he go before he stops? How would you figure out how far he goes before he stops?
Going to 5. 17 going to 5 meters.
No, the 17.5 is here, I want to know where is he at this point out here? Because you were asking about this? That's at 7 seconds. I want to know what is this displacement at 4 seconds?
0. 0. Isn't he at 0?
Not his displacement. Looking for where is he at 4 seconds? His velocity is 0. All right, let's break it down. Very similar to what we did the first time. Just change the problem to what's his displacement after 4 seconds. So, for the first 4 seconds, what is his average velocity?
Then.
So he goes on average 10 meters per second for 4 seconds. What's his displacement? I think I heard 40. So it's 40 meters from there to there. So this is the 40 meter mark. So now I need to figure out what is this distance. What is that distance? How'd you get that?
40 minus 17.5.
Yep. So the total distance the car traveled, well, it's 40 meters to the right, and then travels 22.5 meters back. So the distance traveled, 62.5 meters. We could have also found the average, the 22.5 meters, by looking at the average velocity from stopping to the end of the problem is negative 7.5 meters per second for 3 seconds. So 7.5 times 3 gets you 22.5. And so now finally, the car's average speed.
That's a 62.
That's 62.5. It's the 40 plus the 22.5. So average speed,